incredible Popeye arms would let them grab a prey close in and slash. T-Rex is totally different. It needs open habitat. It's got speed. It's got height. It's got a powerful bite, but it needs room to maneuver. So in an open terrain, T-Rex would beat the megalosaur. But in a barroom brawl in a Jurassic forest, the megalosaur could beat T-Rex.
As Bakker sees it, Megalosaurus is one of the first giant meat-eaters, from which Allosaurus evolved, followed by, on separate continents, Giganotosaurus and Carcharodontosaurus.
The megalosaurs are their own distinct family, but they're very close to the root, the trunk of the family tree of every single giant meat-eater and little meat-eater that came afterwards. They're the patriarchs of these predators.
But T-Rex evolved on a separate evolutionary branch.
I have no doubt at all that Carcharodontosaurus and Giganotosaurus are in the same family. Tyrannosaurus is not only in a different family, but those families are certainly more remotely related to each other. If we look at Giganotosaurus and Carcharodontosaurus, they're like brother and sister. Compare that to Tyrannosaurus, and it's more like a third or fourth cousin.
The older Jurassic giants, Allosaurus and Megalosaurus, were lords of a slowly dividing world.
Dinosaur evolution comes in two acts. The first act, all the world was one stage. If you were a giant meat-eater, a Jurassic meat-eater, a megalosaur, an allosaur, you could walk and spread your genes from one continent to another. Every place had the same fauna.
By the middle of the next dinosaur period, the Cretaceous, the Earth was taking on a more modern shape, splitting into two continents, north and south.
The continents are pulling apart. You can no longer walk easily from Wyoming to South America or Europe to Africa. And that's where Giganotosaurus and Carcharodontosaurus come in. They are Gondwana. They're southern continent specialists. They ruled the seashore, the lakeshore, the floodplains in these southern continents. And in North America, there's very little that's like them.
But Giganotosaurus and Carcharodontosaurus were very similar animals, stocky, narrow-jawed, and sharp-toothed. Too similar for either to have evolved in isolation. This similarity suggests that Africa and South America may have been linked by land bridges long into the Cretaceous, longer than anyone had previously thought. Both Giganotosaurus and Carcharodontosaurus had evolved with the same weaponry, a mouthful of slashing teeth.
These teeth are sharp, are very flat and very sharp. So they work just like knives, just like we use knife for when we are eating a steak. So at the same time, these teeth are very weak. They are not strong. They're not as strong like Tyrannosaurus Rex teeth.
What we're seeing in Giganotosaurus is a mechanism for the animal to come in, basically take a big gouge out of the side of the prey by slicing with its teeth into the side of the flesh, avoiding the bone, and then moving back as fast as it can so that it avoids getting hit or turned on by the animal that it's going after, and then basically waiting to see the effects and then coming in again and again until its prey weakens and falls.
35 million years later, T-Rex was a very different animal. Just as big, perhaps, but with a narrower frame, smaller front limbs, and more robust jaws. With this different body came new weapons, teeth of a very different design.
T-Rex teeth, unlike any other meat-eater's teeth, are huge, swollen, armor-piercing spikes, not blades. They're not knives. These are armor-piercing bullets for cracking and crushing. All of the other giant meat-eaters, all of them, have teeth that are much sharper in the front and back, much thinner side to side. Good for slicing, but if they hit a bone, they just break. They'd snap.
It was T-Rex's massive head and jaw muscles which made it a powerful predator.
Obviously, most of the work that these animals achieved was with their jaws. They were running skulls, essentially, and they attacked with their jaws, and they ripped with their jaws, and they had very strong necks. the arms were sort of a supplemental thing. Skull that I found in the
Running skulls, big and ferocious, but it makes one wonder just how smart these animals were.
And these pieces fit together.
To find out, Paul Sereno looked inside the skull of Carcharodontosaurus.
And if you open up the skull, you'll see the cavity inside where the brain would be located.
They took the skull to the medical center at the University of Chicago.
Now, to get an exact shape of that cavity, we strapped this back together again. Hans took the brain case, the bone, and sent it through a CAT scan machine.
The CAT scan would give them a three-dimensional cross-section of the brain case and information regarding the actual size of the brain.
One thing we can see in the CT data is that when you slice the brain case, you can actually see the inside space for where the brain was occupying. And when you look at that and sort of measure it, you can see that the brain on this guy was actually really small, like very reptile-like. And then you can compare it to other carnivorous dinosaurs.
And what we did is make in plastic, with the CAT scan information, a model of that space, a very exact model, so we can know the shape and ultimately the volume of the space which housed the brain.
But because the cavity was also filled with fluid, the brain took up much less than the total space.
The size of the brain of Carcharodontosaurus is about half the volume of what you see here, less than the volume of your fist.
And it would have weighed in at ½ pound. In order to make comparisons with other species, Larson developed software from the CAT scan data that would give him a 3D image of the brain of Carcharodontosaurus. He then discovered evidence of an evolutionary tie between Carcharodontosaurus and one of its ancestors.
One interesting thing about Carcharodontosaurus is that if you compare it to an Allosaurus, the brain shapes, the brain sizes are virtually identical. And even though you have an animal like Carcharodontosaurus, which is twice the size of an Allosaurus, the brains didn't really change much in terms of scaling.
He compared its brain with a similar image of T. rex's. In the cerebral cortex, where intelligence is centered, T. rex had evolved more and had a sizable advantage.
This area here is where the cerebral hemispheres would have been located. And when you approximate the volumes of each of these two animals, you can show that the cerebral hemispheres in Tyrannosaurus are approximately 50% larger than those of Carcharodontosaurus. A pretty amazing difference.
T. rex's brain was also larger than the brain of Giganotosaurus. If brain size, not body size, were the determining factor, T. rex would remain the king.
Overall, right now it appears that Giganotosaurus did not have a brain that was anywhere near as large as the brain of Tyrannosaurus rex, and consequently we would think that it's a less intelligent animal.
But relative to its huge size, T. rex wasn't a very smart animal. Its brain was smaller than the brain of an ostrich, for example, one of the dumbest birds. What really matters is that all of the meat-eaters were brainy by dinosaur standards.
The bottom line is that you just have to be smarter than the prey you're going after. And again, this is, I think, a little bit more evidence for suggesting that these were active predatory dinosaurs, that they were chasing other animals, because they do have brains that are larger than any of the prey that were around at the same times of them.
T. rex also had another advantage over Giganotosaurus and Carcharodontosaurus: its eyesight. At the Black Hills Institute in South Dakota, fossil dealer Neil Larson has studied the eyesight of some of the largest T. rexes.
The eyes of a Tyrannosaurus rex were probably the largest of any land predator that ever lived. The only animal, there are other animals that have larger eyes, such as the giant squid, Architeuthis, and some whales have larger eyes. But as far as eyesight, this animal had incredibly keen eyesight.
When it viewed its prey, a wide-skulled T. rex, with its eyes further apart, may have had better depth perception, helping it judge distances more accurately. In contrast, Carcharodontosaurus and Giganotosaurus, with their narrower skulls and smaller brains, may have had a harder time figuring out just how far they were from a potential kill. Whatever the differences in their eyesight, all these predators focused on one thing: meat. But were they all deadly predators? Giganotosaurus and Carcharodontosaurus, two huge meat-eating dinosaurs from the south. But does big also mean slow? One clue would be whether the meat-eaters were warm-blooded, allowing them longer periods of activity. To find the answer, researchers in this laboratory at North Carolina State University studied samples of bone taken from various parts of the body of Giganotosaurus.
The reason that we were so interested in Giganotosaurus is that the preservation of this animal is absolutely astounding. One of the things that we need in fossil animals is we need a pretty complete skeleton. You can't do this type of analysis on just bone fragments or bits of bone.
Using a revolutionary technique, William Showers and Rhys Barrick measure the oxygen molecules still present in the dinosaur's bones millions of years after its death.
Okay?
The measurements revealed an even distribution of heat between the outer extremities of the animal and the core of its body. According to their research, Giganotosaurus was warm-blooded.
For the trunk part of the body, where we have our ribs and vertebra and all of our body organs, that there was not very much temperature variability. So the body core of this animal was very constant. So it had a very constant body temperature, and that's typical of warm-blooded animals.
There wasn't large temperature differences like you'd see in a cold-blooded animal. A Komodo dragon, for example, which is a cold-blooded animal, has large temperature differences between its tail and its core body.
And that means Giganotosaurus was like every other meat-eating dinosaur they studied, including T. rex, warm-blooded, like modern birds and mammals.
That means that it could be much more active, it grew fairly rapidly, and it was going to need a lot of food. In essence, relative to modern animals, if we want to make a comparison, Giganotosaurus very likely had to eat on a daily basis the same amount that perhaps a whole pride, maybe 2 prides of lions would have to eat.
In addition, the discovery suggests something about Giganotosaurus's longevity.
It's hard to tell, but it's very likely that these guys lived in the same order of magnitude as modern elephants do. So they could live, maybe 20 to 50 years or something like that, as opposed to living 120 years if they happen to be, with a reptilian metabolic rate.
Although the full lifespan of a Giganotosaurus could have been as long as 50 years, it may often have been cut short by its violent lifestyle.
With all these meat eaters that I have seen, we have now excavated 5 Tyrannosaurus rexes, and every one of them shows healed injuries, broken bones, many broken bones, claw marks, tooth marks. It shows that these animals commonly fought among each other, perhaps for food, perhaps for mating, perhaps over their babies, perhaps over just being Friday night.
To the men who discovered them, Carcharodontosaurus and Giganotosaurus were vicious hunters.
I think that this animal was a predator. I think that based on just the shearing action of the teeth, I feel that this animal was made to grab something actively and cut off an entire limb and just swallow it whole. I don't see it as a passive scavenger.
We are not working with a heavy and slow scavenger, but it was a real hunter. I think that Giganotosaurus was an active predator. I think that Giganotosaurus was unable to break bones and to eat from dead carcasses.
But Jack Horner, one of the world's leading paleontologists, disagrees. Horner contends that the giant meat-eaters, including T. rex, were more often scavengers.
T. rex's arms, first of all, they're the same length as mine. T. rex is 40 feet long and weighed 12,000 pounds and has arms the same length as mine. But when you flesh them out, we find that this much of the arm actually is encased in muscle, and so only